And now I'm going to show you why 6n plus or minus 1, right? And I'll bring back, it's in the book. Nothing I'm telling you here. It's all in the book, but maybe hard to understand, so this is why I've been telling you to it. So switch over here to primes. Here we are. Primes exist as geometric structure in all systems. 6n plus or minus 1 reduced by 5p plus 2p plus 4p through p2 or 1n defines all primes. Now, they will tell you that there is no equation to find all primes, but they're wrong. So, some of you may have heard about a couple of other equations written by some intelligent people, and that's 4n plus 1, right? And 4n plus 3. So, what are those? Well, you'll learn, as has been proven already, that all prime numbers end in 1, 3, 7, or 9. And there's a reason for that. They're odd numbers. And primes can't be even, or they're divisible by 2, and they're not prime. So all prime numbers must end in 1, 3, 7, or 9. That's already known. What this does is give you some equations to help you get there. So 4n times 2 is 8 plus 1 is 9, right? 4n times 2 is 8 plus 3 is 11. So these are ways of finding primes or prime symmetrical numbers. The problem is as I've already shown with 4n times 2, when n equals 2, plus 1 is 9. Thing is, 9 is an even symmetrical number. It's not a prime symmetrical number, which means 4n plus 1 and 4n plus 3 are accurate and will give you primes, but they will give you more than the prime numbers. They will give you even symmetrical numbers that are odd, which sounds funny at first, but 9 is an evenly symmetrical number that is considered odd because it's 9. So, when you use these two, right, you end up 4n plus 1 is 5, and 4n plus 3 is 7, right? So all I'm doing, right, is with my 6n plus or minus 1 is creating a 6n here plus 1 or minus 1. So 6n plus or minus 1 still gets you to 5 and 7, right? Makes sense. 4n plus 1, 4n plus 3, 5, and 7. Only they use two equations. I'm only using one. It's more efficient. And let's try it. 6n times 2 is 12, minus 1 is 11, plus 1 is 13. Both are prime, whereas this showed 9 and this showed 11. One is prime, one is not, right? So mine is more efficient because A, it's one equation instead of two, but every prime number will fall as a, 6n plus or minus 1, period. The problem is you get more than that, right? You end up with some things like 9 showed up here that isn't actually prime, but is still odd, okay? So we call this all prime and prime symmetrical numbers will come from this, right? And all other numbers that aren't this are even or even symmetrical. So technically, this is the base equation, 6n plus 1 or minus 1. Every prime number will be on that list, and I'll prove it to you in just a quick second here. But you also have to do, right? You have to, in order to take some prime symmetrical numbers that aren't actually prime, you need to include 5p plus 2p plus 4p repeated. And this will remove all of the non-prime numbers, or what I call prime symmetrical numbers. from 6n plus or minus 1, leaving only primes. And this is a polynomial algorithm. Okay? This technically is not. So, did I write a polynomial algorithm that can find all primes? Well, yes. But it has additional numbers in there that are prime symmetrical but not prime. And this is what removes those prime symmetrical numbers. So you have all the primes in this, but you have some that are just prime symmetrical. And what does prime symmetrical mean? Well, what that simply states is that there are numbers like P2, right? So 3 is a prime, right? But P squared, 3 times 3 is 9. So 9 is, as I've already said, even symmetrical, not prime symmetrical, right? So what this does is removes all the additional things like 9 from 6n plus or minus 1, which will hold all primes. Now, the reason that this is still a usable, I don't want to say polynomial, but the reason that this is still a usable algorithm, right, that can run in near polynomial time, if you can't write it that way, is because you limit this. Just like 3 times 3, 3 squared is 9. Once you reach the p squared, right, which is p2, right, you no longer have to run this secondary algorithm on the first algorithm. In other words, 3 is prime, but 3 times 5 is 15, right? You'd remove 15, even though it's on the list of odds. Plus 2p, which would be 6, so 21. You would remove 21. This would, if in threes, this would remove 15 and 21. Plus 4p, that's 12, plus 21 is 33. So this would remove 15, 21, 33, and then you would repeat this process just through these again and again until you reach one of two things. There are limits. One is P2. So in the case of 3, it's too small for this to apply. But on larger primes, it will apply. So P2 would be 9 if P was 3, right? Why would we stop there? Why would we stop this algorithm? Well, because anything larger like 27 or any of the others would be symmetrical to 9, not to 3. So you can stop at P2. So you run this algorithm, reduce it by this algorithm through P2, right? The prime number you're talking about squared, or 1n. What is 1n then? Well, if you go back in my theory, 1n is the smallest particles in it's the limit of infinity. Let's put it that way. If 1 is every particle broken down to its smallest, then n is the total number of particles in a system. So there's going to come a point where your mathematics run past the total number of, I'm a physicist, I'm into particles, and I'm into particle physics. So there is no infinity. There's a certain number of particles, and that's it in each magnitude. And that means if you allow your computer to run this forever, it won't run in polynomial time. If you set the limit of P2 or, the other side of that 1n, then it won't run in polynomial time, but it'll run damn close. And it'll prove that you can find all prime numbers. And here's my proof, my visual proof. Okay? I gotta grab my phone here because I don't do math in my head very quick. So let's do this. Let's take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, let's just do some simple multiplication. We know that all prime numbers must end in 1, 3, 7, or 9 because they're odd. And that proves that, all of them have to have that as the final digit. So it doesn't matter what all the other digits are. The last digit must be a 1, a 3, a 7, or a 9 in any prime number. And we know that. So 1 times 1 is 1, times 1 is 1, times 1 is 1. And you'll find that this repeats. So these are all going to be 1s. 2 times 2 is 4, times 2 is 8, times 2 is 16. We're just going to write the 6 because we only care about the last number. 16 times 2 is 32, so we're going to write the last number. 32 is 64. And so you're going to find that any of these end in 4, 8, 6, 2, 4, 8, 6, 2, 4, 8, 6, 2, 4, and it just continues. So any number by 2 will always have one of these as its last digit. Let's do it with 3. 3 times 3 is 9, times 3 is 27, times 3 is, see, here we go, I'm bad at math. 27 times 3 equals 81. 81 times 3 equals 243. 243 times 3 equals 9. And again, so we go 9, 7, 1, 3, 9, 7, 1, 3. This will repeat forever. Okay? 4. 4 times 4 is 16. That's 6. Times 4 is 64. Let's do it again. 64 times 4 equals 256. Times 4 equals 1024. And you'll notice that these all end up in 6, 4, 6, 4, 6, 4 forever. The last number will always be 6 or 4. Let's do it with 5. 5 times 5 is 25. 125. 625. They're all 5s. Okay? 6 times 6 is 36. 36 times 6 equals 216. 216 times 6 equals 1296. And again, these are all going to be 6s. Right? 7. 7 times 7 equals 49. 49 times 7 equals 343. 343 times 7 equals 2401. 2401 times 7 equals 16807. 16807 times 7 equals 9 again. And again, 9, 3, 1, 7, 9, 3, 1, 7. This will repeat forever. 8. 8 times 8 equals 64. So that's 4 times 8 equals 512. 2. 512 times 8 equals 4096. 4096 times 8 equals 32768. 32768 times 8 equals 262,144. So we're back to 4, which will then go to 2, 6, 8, and this will repeat forever going this way. Let's do it again with 9. 9 times 9 equals 81. 81 times 9 equals 729. 729 times 9 equals 6561. So this will go 191919 forever. 10 will always end in 0. 10 times 10 is 100, times 10 is 1,000. So these will always be 0, 0, 0, 0, 0, 0. 11, let's do it. 11 times 11 equals 121. Times 11 equals 1,331. Times 11 equals 14,641. So you see these all end in 1. 12. 12 times 12 equals 144. Times 12 equals 1728. Times 12 equals 20,736. Times 12 equals 248,832. 2 times 12 equals 2,985,984. And this will then be 8, 6, 2, and this will go on forever again. So why would I be doing all this? Why is this important? How does this function? Well, this is a matrix of numbers by multiplying them against themselves and basically squaring them and seeing what the resulting last digit would be. So why is this important? Well, we've already defined up here that 6n plus or minus 1 will define all primes when deteriorated by this through p2 or 1n. This is true because the last number will always follow these patterns. So what are we going to do? We're going to take this duodecimal system, this duodecimal matrix, duodecimal for those of you who don't pay attention, or 12, so a system of 12, and we're going to fold it back on itself to extrapolate it in base 6. So what is base 6? Well, if you look at the surface of a clock, you get, it's base 12, right? So we're going to extrapolate in base 6, which is just 1 through 3, 4, 5, 6, and then 7 would be 1 again, right? So 1 and 7, 1 is all 1s, which means, remember, all primes end in 1, 3, 7, or 9. So all 1s would then match with all 7s because 7 is 9, 3, 7, or 1. 8 would be these numbers, not prime. 9 would match with 3. 10 would match with 4, can't be prime. 11 would match with 5, right? End in 1. But 5 and 1, being 5 and 11, are even symmetrical. They're magnitudes. And they don't create primes. And 12 would then be with 6. None of these could possibly be prime. So when you take this duodecimal system and you fold it back on itself, 1, 7, 2, 8, 3, 9, 4, 10, 5, 11, 6 equals 12. Well, this means that there are 6 possible lines, and the only primes can be on 3 and 9, 1 and 7. Which tells us what? Well, that tells us that out of 6 possible pathways, primes will only fall on 1, 7, 3, and 9, which are exactly 1/3 of this system. 1, 2, 3, 4 can't be prime. 2 can be. So 2/3 of all numbers are even and even symmetrical, and 1/3 of all numbers are prime or prime symmetrical. Well, where have we seen this before? Remember my orbital field, right? No third, 1/3, 2/3, and 3/3, right? Which tells us numbers fit within 1/3 and 2/3 of this system. All prime and prime symmetricals are 1/3, okay? Because they fall on 2 out of 6 lines. And all even and even symmetrical are 2/3, or 4 out of 6. None of the numbers that fall on these lines, as you extrapolate them outward, could possibly be prime. So all primes must fall on 1, 3, 7, or 9, which are only 2 out of 6 possible in a base 6 system if you take a duodecimal matrix and fold it around on itself. So 1/3 and 2/3.